Ladies and gentlemen, welcome. Welcome to the Epic Online Technology Meeting with the whole supply chain of imaging and camera systems. It's September. It is the middle of September. It is sunny in the Netherlands. It looks great. Let's have 2 hours of spectacular business decision making. Weekly Epic Online Technology Meetings continue, and on Monday 14th of September, the topic of discussion is vision and imaging systems. Machine vision and photonic sensors have never been more important than now in modern manufacturing. Today, cost-efficient CMOS and CCD sensors have established a satisfied customer base in automotive, pharmaceutical, packaging, and food and beverage. But this is just the beginning of a revolution. There is a growing demand by manufacturing companies for precise monitoring of their processes. This includes gas exhaust, chemical compositions, counting throughputs, monitoring vibrations, analyzing changing colors, measuring defects, monitoring water quality, and the list goes on. The result is cost-efficient manufacturing with minimal waste. We need to look farther than the visible, from short wavelengths to the long infrared, with hyperspectral and multispectral cameras, and include distance measurements while treating the data collected with artificial intelligence. I expect companies like Speaking, Applied Spectral Imaging, Norsk Electro-Optic, Resonon, Telop, SpacePec, Cubert, Teledyne, Xenics, and their supply chain answering the epic question to the manufacturing companies, many present in the room. So watch us very closely on September 14th at exactly 3 p.m. Central European Time. So here we are, exactly at 3 p.m. Central European Time, and thank you so much for the interest that all these online technology meetings are bringing to the community. I have to say that right now we have already grown to 600 members, and we cannot be happier about this. These meetings cannot be done without your support, and for this, from the bottom of my heart and the bottom of the Epic team's heart, thank you so much for keep supporting us. The online technology meetings were an idea of the COVID-19 times, and we realized that it was the perfect tool for bringing together different companies only using 2 hours of your time. So we start at 3, and at 5 o'clock, all of you can go back to your families or your office space, wherever you are. Today we have the episode 3 of season 2 of the Epic Online Technology Meetings. As I keep saying, we have one per week now because I know some of you are starting to travel. Please keep attention to the calendar, and whenever you see that an event is interesting for you, just send us a quick email and we'll make sure that we position your company properly in the supply chain for that particular meeting. I have to say that Epic is not only Elena, although she's fantastic. Epic is definitely not only me. Epic is 600 company members who tell us what to do. And they tell 15 people, 16 people, half of them with PhD positions, who understand what every company can do for each other and how to actually connect. And all our business is to connect companies. So expect all of you who are in the Zoom channel, expect a lot of email introductions after this meeting. As many of you already know, Epic organize events, but Epic, most important, provide access to a network of companies, a network to investors. And now we even have the biggest in the world, Elena, the biggest in the world website to find a job in photonics, jobsinphotonics.com. If you're looking for a job or you have opening positions to be filled with photonic experts, go to jobsinphotonics.com. I also would like to remind you, many of you, I think actually most of you are Epic members, all of you have access to a long list of market reports. So if you're wondering about the next market trends, just look at the top left corner of the Epic website, extranet. If you're an Epic member, you can download, I think it's now 15,000 view graphs of market data. And now we move on. Let's talk today about vision and camera systems. This meeting would not have been possible without the support of our sponsors today. I would like to start with Imasenic, all the way from beautiful Barcelona, develop CMOS sensors. It's one of the most innovative company on making large volume, affordable CMOS sensors for process monitoring. AEMtec. AEMtec, whether you're looking for backend processing or a production partner of camera subassemblies, AEMtec is really the place to go. Actar Advanced, you're looking for black coatings. If you're looking for black coatings, after advanced coatings, they make the perfect black coatings for your application, full absorption Chroma. If you're looking for an optical filter, don't go any further. Chroma, in my opinion, they make the best optical filters in the market. Duma Optronics, all the way from beautiful Israel. I hope the situation gets better in Israel. Good luck with the next few weeks. Duma Optronics is the key company in EPIC on automation for testing and metrology in optics. If you are ever looking for also building an optical instruments, have a chat with Duma Optronics, a key company in the assembly and testing of any optical instrumentation. Caeleste, all the way from beautiful Belgium. If you're looking for beyond state-of-the-art CMOS sensors, these people love to receive crazy ideas and discuss them with you. So anything from an image sensor to any photonic detector, talk to them. Actually, I talked to them earlier today. They told me that they already have CMOS sensors in 10 different space missions, and asphericon, the most precise optics you can find right now in the EPIC network. They are manufactured in Jena, where else? And they are manufactured at Asphericon, freeform, aspherical lenses, you name it. These people are the ones, whenever your typical values for resolution are as high demand as they can be. All these people are great, and you know who is also great? Dr. Elena Beletkaia, our technical expert for medical and imaging technologies. Elena, thank you very much for being with us this afternoon. Tell us, what's in the menu today?
Thank you, Jose, very much. Well, thanks everybody for joining this meeting. We have a great agenda today. We will start with an overview of the industry in general. We have a few end users who will share their experience and hopefully also really challenge the supply chain, which we have in here. We'll have a bit of a solutions within the presentations, and obviously we hope to find a lot of new solutions, businesses and collaborations through the whole supply chain, through all the camera manufacturers, components, optics, optical instrumentation, metrology. All of it is present in here. If it's not here yet, then there is R&D who can research and find and make it for you. And there are system integrators who can put it all together for you, and even further market intelligence and investments. We have it all in the room. So please don't hide your faces, just show yourself, speak up, and be part of this meeting.
Thank you so much, Elena. This meeting is also live streamed in YouTube. So I'm going to say hello now to the YouTubers. Hello, YouTubers. If you want to connect with any of the companies in the meeting room today, any of the companies in the Zoom channel, all you have to do is send me an email, jose.pozo@epic-asoc.com, and I will make the introduction. Also, you have questions, please feel free to post them in the YouTube chat. And for the people in the Zoom room, this is also valid. Please feel free to use the internal Zoom chat to talk to each other, do business. But if you want to connect with each other afterwards and you don't have the email address, all you have to do is send me an email, jose.pozo@epic-asoc.com. I will be more than happy to make the introductions, because I've done something like 500 introductions since the EPIC Online Technology meeting started, and I don't get tired. As Elena knows, I don't drink only water, I drink lots of coffee. And let's start with the meeting right now. Let's go to one association that will drive, already driven the vision system, but will drive with EPIC the connection between photonics and the image systems. Nobody in the world can do anything alone anymore. EPIC has partnered with EMVA to make sure that we get the right value to the EPIC members and all the people in the EMVA membership and network. Thank you very much for being with us this beautiful afternoon. Tell us how we are going to help each other. Chris Yates from EMVA.
Thank you, Jose. Thank you, Elena. Hopefully you can hear me and see the screen.
Loud and clear and crystal clear.
Thank you very much. And also thank you for the invite here to speak at this great meeting and to be able to cover it. So I would like to introduce the EMVA, which is the European Machine Vision Association. I am the current president. Professionally, I am also a director at Vision Ventures, which is a member of EPIC, which is a mergers and acquisitions specialist advisory. So my main aim here is to provide an introduction to the EMVA and also to pull on a few themes in vision technology, since I'm not representing one company, that I think are of interest to the group here. So firstly, the European Machine Vision Association. So we are representing more than 125 members. from over 25 countries. We are open to anybody that has an interest in machine vision. We are a not-for-profit organization, we're non-commercial. We are owned by our members and the operation is coordinated by the board of directors and our general manager. Whilst we are called the European Machine Vision Association, we have members from North America, also Asia represented, a global organization. Importantly, we are the host of 4 international vision standards. Standards are a very important topic for allowing disparate systems to come together and work well to provide value to the end user. And we're really dedicated to the promotion of vision tech, strengthening competitive of our members, cooperation, standardization, and information. I'll show our logo board here. It is not quite as large as the EPIC one, but I think you'll appreciate the color coordination that we put together on ours. So this is 125 members. You'll see there is some overlap in terms of members of EMVA and EPIC. So for instance, companies such as Opto, AMS, Prophecy, Xenics, who I think we'll be speaking later on, are also contained within EMVA. Vision applications. Now, Jose did a fantastic, very quick overview of multiple applications. Really all I wanted to say here, the vision sector is often associated with factory automation. However, there are many application areas and industry verticals that are applying vision technology. In some ways, it is a horizontal technology. Here you have some applications, of course, the robotics, manufacturing, electronics, but also some high growth areas such as logistics that's seeing great opportunity for including vision technology. One of my favorites in agriculture and the use of vision for precision agriculture, and of course, aspects like automotive and defense. All of these are using vision technology components. I wanted to give a very quick overview of the kind of typical components of a vision system here. So these show some components, all of which are provided by European Machine Vision Association member companies. They're really typically used to pull together to make a typical machine vision solution. So starting from the left, we have the ones that are possibly closer to EPIC's heart in terms of the illumination, providing the initial photons if ambient light is not sufficient to provide light to the application, lasers, LEDs, etc. Lenses are very important to machine vision solutions, both for directing projected light and as well as ultimately forming images to the imaging systems, which are most familiar in terms of cameras that you see in the middle here that are charged with converting that photons to electronic image. As we move further to the right, we have closer, I would say, smart cameras and sensor systems that provide some additional onboard functionality. And then towards the more embedded components like frame grabbers that are responsible for capturing and buffering high data bandwidth vision systems. And then the processing of this, which I'll come back to, with dedicated vision boxes. And of course, all of these systems wrapped together with software libraries and software components. This is not the complete extent of a vision system. They're typically arranged into a machine by a system integrator or machine builder before delivery to an end customer. But it gives you a flavor of the types of products that are provided by our members and that are typically required to be touched upon in a typical vision solution. So with the final 3 slides here, I wanted to touch on 3 aspects of vision technology that I see as important for the future. So the first one is the types of imaging that's available now. So typically when people think about imaging technology or machine vision, they think about a grayscale or potentially a red, green, blue or RGB image, as you see on the top left here. But we are so lucky that the extent of imaging technologies is continuing to expand, and it's continuing to expand as cost is being reduced. So for instance, we have multispectral systems, hyperspectral systems. I know we'll hear from Cubert later in the talks. We have the shortwave, midwave and longwave IR, again with several companies really addressing the cost points of pushing that down so that it can become wider adoption. And I would say, as an ex-chemist, a very nice overlap between hyperspectral and midwave IR in terms of the potential for imaging fingerprinting. We have new technologies such as polarization imaging now becoming into standard sensors that allow for visualization of stresses, strains, difficult specular surfaces. 3D is a very large and interesting topic in itself, particularly with the overlap to technologies such as robots and AGV guidance, and the ability to look to image in 3D, whether this is by profile or whether by its area snapshot. And then also there is acoustic imaging, a non-electromagnetic type of imaging, but again providing a different information set, and also radar imaging. There are other types of imaging I could have put on here, such as X-ray imaging, etc. And all these are becoming wider available, and all ultimately provide raw, spatially correlated data for processing. So the second topic I wanted to mention was processing. So the central proposition of machine vision is that I'm able to capture raw data, apply processing to it of some type, and extract information out of this, whether this is information to be used by humans or whether this is then to be used by downstream machines for further automation, etc. Now, we have a tremendous amount of data available, not just the modalities there, but even if I think about a typical grayscale image sensor, say a 12 megapixel image sensor, typically now I can buy this running at 300 frames per second. This will produce something like 7.5 gigabytes of data per second, a tremendous amount of data. And then this opens up challenges in itself of how to process this data to extract the information. And this leads to a number of questions when thinking about processing, such as how much do I need to process? Can I put this data actually across some network or connectivity cables? Can I process this near to the image sensor on board? How quickly is the information required? Which leads into aspects like latency considerations. Can I pass this data all the way up to the cloud, expect a latency of 2 seconds before the image is required? And this partitioning of processing across from right next to the image sensor on the camera at all the different stages up to the cloud is a really important aspect of system design that should be considered. However, we are fantastically lucky again that the available processing power and cost of processing compute is phenomenal. I mean, it's being driven, of course, by the mobile industry. The final point I want to bring out in terms of a theme is AI and deep learning. So this is really the direction towards neural network approaches for image processing. And this has been really a tremendous success in a very fast moving area within the last 5 years. I think within the last 8 years, you've seen this move from not academic curiosity, but the realm of either large consumer giants such as the Googles and the Facebooks and academics to being really deployed by pretty much every company that's developing machine vision solutions. It's really been enabled by, again, the power and the cost and availability of processors, typically GPUs, and now many types of different AI-specific processors, as well as freely available tools and architectures that we can all download, for instance, TensorFlow from Google or PyTorch from Facebook. This is an extremely active area for companies, also from strategic investment points of view, very active for venture capital, startups, universities, and at the other end of the spectrum, mergers and acquisitions. On the right-hand side, I'm briefly showing the kind of generic process where we assemble a typical data set, we configure a neural network, then these are trained, typically in a separate set of compute off-site or off things before validation and then deployment to wherever the neural network should be operating. This is a trend I think is not going away. This is a shift of a paradigm in terms of how vision solutions are put out there. So with those 3 topics, I will close. Hopefully I fitted in within your 6 minutes, Jose. My details are here on there. Please feel free to contact me if anyone would like a steer into the vision community in any way. And thank you again for inviting me to this talk.
Thank you very much, Chris. Thank you for a great presentation. Unfortunately, your work is not yet done because now it's the most beautiful part of every presentation, which is the discussion. You are both the director of EMVA, but also, as you said in the beginning, EPIC member and investor in camera systems. I read between the lines a lot in your presentation that there is a huge push for the AI software intelligence software-driven intelligence on the camera. Is that a tendency? Are the investors more looking at the software than the hardware part of imaging systems?
There's definitely a shift as hardware becomes available at lower cost, which is what always happens. There's definitely a push to focus on more value on the software. However, it isn't as simple as to say I can put all of this application down onto a camera, onto a specific part of a compute, because by doing this, I've necessarily reduced the applications that I can address. So typically what you will see is a split between a vision system that's being assembled by specialists where they want to address a bespoke application, and then those applications such as completeness detection being adopted by large sensor providers such as an IFM or a SICK or an Omron, where the actual application is such that it can be embedded down into a sensor system. And the AI processing one just adds another level of convolution within this in terms of, can I actually process my inference engine on board the camera? But look, we're fantastically lucky. We have the tools available. We have the components. We can do this. All we have to limit it is by our ingenuity.
One thing that is interesting, you say the components are getting cheaper and cheaper, but one of the biggest pushes that I have seen from the photonic side is hyperspectral imaging. And when you talk to many end users of hyperspectral imaging, they keep telling that the biggest drawback is actually the price. Is there a bottleneck? Is there a roadmap there that the EMVA or the members or your friends are trying to do to challenge together this important bottleneck?
I think we have, within the EMVA, I think hyperspectral is an interesting point because you've raised the cost barrier. And if we think about traditional hyperspectral as is done with a push broom scanning mode, there is certain costs that are contained within there. I think there's actually two barriers with hyperspectral. Cost is definitely one which you can address in one way, and you look at the directions in terms of putting filters down on an image sensor. But there's also a complexity issue with hyperspectral. It is a bit like 3D data, that sometimes it is complex for people to understand how to process that data to get the information they want, particularly at the end users. So I actually think both of these are important. The reduction in cost for the components, potentially through reducing modalities, potentially by throwing in computational techniques, but also wrapping the applications such that some of the complexity of the data is somewhat not hidden, but is wrapped for the end user.
One final question from my side. Of course, if there are questions in the room, just raise your hand. We have a lot of companies in EPIC who made image sensors, who made CMOS sensors. Today, for example, you have companies like AMS, Caeleste, Imasenic, Emberion in the room. Many of their customers are in your membership. What kind of words of wisdom, what kind of ideas can you give them to give the technology to the right market segment in the current imaging landscape?
Yes, and I think it's interesting you've mentioned three companies that are addressing three different parts of the market with three different business models. What I would say is the image sensors we are working with, some of the value will be in the specialisms that you can provide for this. None of these companies are looking to compete with the Omnivisions of the world. So, for instance, I know Caeleste is an expert provider. If I want to make a specialist design that I have an idea for, I can come to them as a fabulous design house and they can work with me to do that. I know Emberion is making good strides, and I'm looking forward to the results of pushing down the cost of shortwave IR. And AMS, well, actually in its acquisition of Semosis, provided me with the example of the 12 megapixel running at 7.5 gigabits per second is image sensors I know well. I think within this sector, focusing on the value and not trying to compete at the very consumer end, of course, is valuable.
Thank you so much, Chris, for being with us this afternoon. Do stay with us, and anytime you have questions, please ask. Together, you and me, we're going to make sure these people do business. And today we have a great agenda. We're going to go to hyperspectral imaging. We're going to go to a company which I love. We're going to go to Resonon. The president of Resonon, Rand Swanson, is with us this beautiful afternoon in the Netherlands. Rand, what time is it over there?
It is 7:24 in the morning.
Good morning. Let's have a good morning coffee, and the floor and the attention of everyone in the world goes to you.
You have to bear with me just a minute, make sure I can share the correct screen that is hopefully in presentation mode.
Let's see.
Does that look right?
It looks fantastic. The floor is yours.
Okay, and hopefully I've got the right animation presentation up there, and I will keep it simple and short. And because I think most of your viewers are experts and know what I'm talking about. And so I was told to present a slide that says what we do. And we do hyperspectral imaging. And in brief, that means we do push broom version in our company where we take each pixel and we basically run it through a diffractive element. It's not a prism, but that's just so we can see it. Or another way of thinking of it, for the data, we provide a complete spectrum for each pixel in the image. And let's see if I can get the, it looks like I'm not getting the animation to go. Let's see if we can make the animations work here, people. Sorry about that.
Normally the space bar always helps.
Space bar, there we go. Thank you. All right. And so basically what it's about identifying materials. And colors are materials, and that's what we're looking for from a very simplistic high-level point of view. So, and what do we offer? Resonon offers hyperspectral imagers themselves, and as I mentioned, they're push broom versions. We have software solutions both for researchers and for machine vision, and we provide some integration services, both airborne, machine vision, and research. That's it in a nutshell. We're vertically integrated. The thing we pride ourselves on is that we pay particular attention to is the signal to noise ratio. We concentrate on providing high quality data. Hyperspectral imaging will sometimes get the rap that you provide hundreds of channels of noise rather than hundreds of channels of good data. And so we concentrate on getting the data good and have a strong emphasis on the signal to noise ratio. What do we look for when we're going forward? When we're looking for applications, we look for applications where materials or color matters. As an example here are, I think you can see two different colors left, and we classified them on the right. And this is for the very important application if your child comes home and mixes up the candies and you need to separate them. I hope you understand that's a joke. The applications are everywhere, and that's actually part of the problem. Food, agriculture, recycling, pretty much everything you can think of where color or materials matter, and you need to distinguish within a flow of materials, it can be used. And that's both a good thing and a bad thing in that you can apply it everywhere, but it makes it very difficult to find a correct focus. And what we look for moving forward, and we're making some progress in that, is we're looking for integrators that know what they're doing and have relationships inside specific industries. We're finding breaking into new industries is very difficult. And many of the bigger industries don't trust people that they don't know. And so having a known integrator is crucial to breaking in. And the previous speaker mentioned the two problems. One was price and one was complexity. And I'll speak to that just very briefly. In price, hyperspectral imaging is certainly more expensive than regular cameras. Although for industrial applications, you will see that it pencils out very quickly. And so I've been baffled how come even with very quick payouts, often under a year, we still don't get the hits that we sometimes think we should. And we think it has to come down with the complexity, and not so much with the complexity itself, which we can address, but that the industrial users don't really believe it. And if they're going to spend a lot of money for a solution that doesn't work, that's a bad rap for them. If they were confident it would work, it pays out quickly. And so that's one thing that we're struggling against. And one thing we try to do to address that is of course prove it in specific applications. The problem we've run into as a company with proving it with specific applications is every time we have a good success story, our customers go, no, you can't tell anybody about this. And then we have trouble spreading the word. And so we have to be very careful about what we say about what our success stories are. but we have probably, and we're small, but over 100 successful machine vision deployments, all of which I can't tell you about. And with that, I'm going to end my presentation and let you move on with your program. And if I can find out how to stop sharing, perhaps you can help me, Elena. Thank you.
Okay, thank you very much for your presentation, Rand. That was great. Feels very weird not being able to clap at the end of the presentation. Yeah, also thank you for the joke. That makes it nice. But if we go no joke, we go to epic question actually, which goes following what you can do for them and what they can do for you. So what do you search for in the community, in the supply chain?
In the supply chain, one of the things was mentioned, one thing we're looking for is inexpensive shortwave infrared cameras. Now, we're actually good with the indium gallium arsenide cameras that are out to 1.7. Those are quite good, and the price is acceptable. The bigger challenge is to get the full shortwave infrared out to 2.5 microns, 1 micron to 2.5 microns. Big problem there. The cameras we get are expensive, and the reliability is imperfect.
Okay, and we now start getting some questions also from the audience, which is great. Thank you. Keep coming. Jan, would you like to announce your question yourself? I think you have even a couple.
Okay, yeah, fine. Thank you very much, Elena. My first question was, in fact, what is, let's say, discriminating you from Headwall and Specking? Because those two companies are pretty well renowned for imaging hyperspectral images.
So Headwall and Speckum are two primary competitors. I look at this, in my opinion, we have slight variations on our technology. I don't like to say anything bad about our competitors. The way I look at it is we are all adventurers in a new land. Hyperspectral imaging, in my opinion, should be an industry that's 10 to 100 times bigger than it is now. And we're all trying to get over this technology barrier, why it isn't adapted to where it's on all sorts of instruments. Is something that I've been perpetually confused about. So I think Headwall and Speckum are both good companies. I think they have a good technology. I think our technology stacks up very well with theirs, and I wish them the best. And I look forward to competing with them. But I think we're not so much competing head to head as in different opportunities. That when they have a success, it's a success for us and vice versa, because really the technology hasn't been exploited to the extent I think it should be. I don't know if that answers your question.
Yeah, thank you very much. And then I had another question. In fact, yeah, as Jose already introduced, we are making image sensors custom designed. So suppose that you can dream your ideal hyperspectral imager. What should you quote?
What should you, the ideal hyperspectral of cost?
No, not of cost. Before, let's discuss first what are the features you specifically like there.
Okay, so right now, in my opinion, what is the, let me rephrase your question so I make sure I answer the question. You're asking, what is the ideal hyperspectral imager?
Yes, indeed.
Okay, right now, there's an imbalance with hyperspectral imagers between spectral resolution and spatial resolution. Typically, one wants more spatial resolution than typical hyperspectral imagers provide and less spectral information. Most of the spectral features you're looking for, which means how fast the color changes, we have way more resolution than needed. So we end up with a lot of noise because we're dividing the spectrum into too many channels. And so we're taking steps to move forward to switch to make a trade-off to provide less spectral resolution and more spatial resolution. And right now it's difficult to hit the sweet spot that's more spectral resolution than typical multispectral cameras that don't have enough spectral resolution, and hyperspectral cameras that have too much spectral resolution. And it's a sort of a fundamental engineering limitation of which I would bore everybody here talking about it, although I'm personally very excited about it. But what we're moving to do is try to get more spatial resolution, less spectral resolution. You really only need about 5 to 10 nanometers of spectral resolution. And hyperspectral imagers typically are down in a nanometer or maybe 3 or 4 nanometers spectral resolution. And that's much more than you need.
Let's say at a certain moment, I guess you can also trade in, perhaps optical complexity versus cost of the silicon, if we limit ourselves to silicon. You have also, let's say, those solutions with, say, up to 60 or 128 spectral bands in, let's say, clusters of pixels. Do you see that as let's say, interesting solution for you?
That is, so you're talking about basically binning on chip. Is that correct? Yep.
Okay, so, on chip or off chip, but where you acquire, let's say, all channels simultaneously, in fact, for a 2D image.
Right. And so, and this may get more technical than I think some of the audience wants. Binning on chip is a great thing. It helps speed. It basically provides more detector area. And if you put the right optics in front of it, it's some real advantage. One problem we have with binning on chip is that that we end up saturating the A to D converter. Basically, we want to use the full well depth of every pixel to maximize our signal to noise ratio. And when we bin on chip, if the A to D converter is set for a single chip for saturation, you saturate your A to D converter and you limit your performance with on-chip binning if you're not careful.
Okay, Rand, thank you very much for this. We can go deeper into discussion later in the meeting. We still have some more questions going on, also from Andres from SE Optics. So Andres,
hi.
Would you unmute yourself? Yes, thank you.
Can you hear me okay?
Yes,
I can hear you.
Great. So I'm looking at my camera and I see that I need a haircut, so I'll have to make an appointment for tomorrow. But anyways, very interesting. And that last question actually led perfectly into what I wanted to ask about, which is, are you finding the right optics to go with all these incredible sensors that are coming out into the market? You're talking about spectral ranges, as you're going to multispectral, hyperspectral, all these many spectral, the color correction through these wide bands becomes difficult. Are you having good solutions there? Are you needing improvements in the optics as well? It's just, open to the question if you have some ideas.
Sure. So one of the reasons push-beam hyperspectral imagers are expensive is because you do have complicated color correction that you need to deal with. The approach we're taking, which we have patented and I can talk about it, is we actually need to break up the symmetry and not use circularly symmetric optics. And so we're using, for example, parabolic cylindrical optics that allows us to trade the spectral resolution for the spatial resolution. In other words, provide better signal to noise with fewer spectral channels. And with that, it is still more expensive. We're finding good optical solutions, but right now the supply chain isn't so much how good the optics are that we're getting, but how quickly we can get them. We need to have pretty high inventories because we need to figure like 6-month lead times to get the optics we want. And that tends to be the part that eats up a lot of our cash just because we have to have significant inventories due to the long lead times for optics.
Okay. All right, thank you. Appreciate it.
Okay, great. Thank you very much for this question as well. As we were discussing before, the ideal hyperspectral camera and the ideal setup. I mean, nothing can be ideal in a camera, especially when we talk about hyperspectral, without proper setting of filters. And with that, I would like to ask Greg from Chroma to maybe introduce himself. Greg, would you like to introduce yourself and say a few words about Chroma? And we would need you to unmute for that. I'm not sure if Greg hears me. Greg?
I think you're looking for George from Chroma.
Yeah,
George,
okay.
George Roth, how are you doing?
Oh,
You look
sorry.
fantastic with these beautiful mountains behind you. Where is this picture taken from? Where is it? Where are those mountains? Most important.
Right behind me. No, these are from one of my summer hikes in Bavarian Alps. No, that's Austria. I have to admit that's Austria.
Okay. Well, what do you want to tell us? How can we get the best filters in the market?
Just contact me. No, I'm sorry. I was just a few minutes off the meeting. So can you repeat the specific questions from the last discussion, and I can give you a precise answer?
We were told that you wanted to share with us one slide about the potential technologies that you want to bring from Chroma to the camera system. So we can come back to you at a later part of the meeting if you want.
Well, I can give you a quick answer. So I think we at Chroma, we're using the state-of-the-art sputter technology to coat filters in an area from 190 to nanometer to 3.5 micrometers. And if we talk about the keyword hyperspectral imaging for filters, there's in many cases this confusion that you need the whole spectral range filtered for hyperspectral imaging. From the projects we working with customers on hyperspectral imaging, in most cases it's only a few bands or windows from the visible or the sphere range required to be filtered, and other portions of the light to be blocked. And this is what we can do custom according the specific needs for the project and the camera technology behind it.
Excellent. I keep saying whenever you have any kind of challenge for filters, especially continuous filters, the hyperspectral imaging one, or any other filters, George is the right contact. I love when in epic meetings opportunities for collaboration happen, and my friend Jiri from Emberion has posted something very interesting in the chat. I want to hear it. Apparently there is some room for cooperation here. Jiri, what did you have in mind?
Yeah, sure. Thanks. You, Rand, you were mentioning that about 1700 nanometers an issue for you. So Emberion, we are working on our own nanotechnology sensors and also building camera cores around them. We will be providing from 400 to 2000 nanometer initially. Later, when we get everything up and running, also higher. So I guess we might be worth of talking. I could share some of our current data sheets, and of course, if somebody else is also interested in wider spectral range, more than happy to have a discussion. So technology is our own in-house nanotechnology, and perhaps a bit different in many senses than the existing ones.
Great, thank you.
Thanks.
Ran, do not answer yet. Keep the answer for later. There's a lot of opportunities for collaboration here. Let's continue and let's go now to the end user. I want to talk to Universal Robots. I want to understand how we can place our cameras in the vision system and machine vision work areas. So I have here with us Mark Ray, Sales Manager for UK and Ireland of Universal Robots. Mark, thank you very much for being with us in this beautiful afternoon. It's 3:43 in the Netherlands. It's 2:43 in the beautiful UK. The floor and the attention of everyone is yours.
Thank you. So thank you for letting me speak to you today about our collaborative robots. I just need to get this to go from there. from the beginning. So Universal Robots is a Danish company. We're based in the town called Odense. It's about 2 hours from Copenhagen. And this one small town is only famous for two things. It's the birthplace of Hans Christian Andersen, and there's more than 100 robot companies based in this one small town. And we were the inventors of collaborative robots, and our inventors were 3 university professors that were looking at why companies wouldn't use robots, wouldn't adopt them more. So they set about solving the 5 key reasons that they found. They wanted to make robots that were easy to program, quick to set up, and they could be flexible enough to be moved around the factory to given different tasks. And by being collaborative, that means that they can work alongside people without the need for machine guards. So in vision, if you wanted to move a camera or fly a camera around a part, it makes it very, very simple to set up without having to have cages around the robot. We do that by monitoring the force in the joints of the robots continually. So it's part of our safety architecture. And if the robot bumps into something, we immediately put it into a safeguard stop. So it's a kind of, not emergency stop, but a kind of nuisance stop, if you like. And we also got a very, very quick payback. So generally on a task, if a robot is going to be doing a sort of task that a human might do, you'd get paid back between sort of 9 to 12 months. So this is why it's attractive for industry, because it's a very, very quick payback. So these are the robots that we make. There are 4 robots in the family. The number of the robot denotes the payload. So we have a 3 kilogram, a 5 kilogram, a 10 kilogram, and a 16 kilogram. They all have different reaches, and they can be linked into other devices really simply and set up really simply. And the main application benefits for using them with vision is that we have a programming interface that we've written called Polyscope, which is already on the robot. It's a menu-driven system that you can pull out templates and actually hand guide the robot where you need it to go. Once it's in position, you can record that position. So to set up a simple pick and place takes literally 5 minutes. You don't need machine guarding around it because we have the constant force monitoring it. And we pride ourselves on our repeatability. So for a robot, and certainly a collaborative robot, our 2 smaller robots are down to 30 microns, and the 2 larger ones are to 50 microns. It's a very small footprint, so it can fit on machines or within processors very, very simply. And one of the videos that you watch online, you'll see that it takes less than an hour to set it up out of the box. So the robots come preloaded with software and pre-calibrated. And they've got really easy systems to set up to communicate to other devices. So we have digital inputs and digital outputs, so we can give the camera system a trigger, wait for a wait signal back from a camera to say it's been a successful inspection. And we've also got an Ethernet port on there, and we can link in directly to pieces of software from Cognex. And there is also something called a UR Plus scheme with all the compatible camera systems that will work with the robot. So the buffer piece of software that sits between the robot's operating system and the camera system has been written to make it compatible. The real benefits here is it gives you an ability to get a clear field of view on a 3D object and control the lighting. So you're actually getting a better craft of an image. And with some examples here. So comprehensive logistics are a just-in-time manufacturer for the automotive industry. And they make a steering subassembly that goes next door to one of the automotive plants. And they wanted to improve their inspection because they had human inspection currently. And there was a safety critical component on there that we wanted to check the plug was in place. It would actually activate the steering lock if this wasn't in correctly. And they also wanted to reduce costs and make it just in time. So what they did is they mounted a camera on the end of a robot and drove it round the assembly. So it carries out lots of different inspections. And if they wanted to add in an inspection, it's a really simple thing to do with the robot. You can guide it to a new position and then get the robot to trigger the camera from that position. So it's a completely 100% inspected cell now, and they record all the results from each camera inspection and also the position reference from the robot as well. Again, the inspection time of this is a constant. So as opposed to a human, you might have a person that takes longer to do the inspection than another person. The robots is constant. So they can access that and reduce the takt time for the production line. It gave them the flexibility to add inspection points into this assembly. I think originally they started with 10 inspection points, and now they're up to sort of 16 inspection points. And again, because it was over 3 shifts and it was taking a person out of this particular role, it actually paid for itself within 4 months, and it increased their quality throughput as well. We also have robots in BMW, and this is a picture of 4 UR10 robots with 3D scanners based on the end of the robot, and they're being driven over the bodywork to look at panel gaps at critical control points. And once those measurements have been taken place, they send that back to their central MES system. So as you can see there, the 4 robots are all working in harmony on this line. And what they actually managed to do is to get the repeatability down to 50 microns. They reduced this inspection time by doing it automatically. And these robots also gave them a lot of data analysis that they could actually use upstream further in the process. Again, it was a really quick payback system. So these robots fly the cameras around to the different points on the panel gaps, the lines converge, it does its measurement, and it's being triggered by the camera. And once it gets a signal back from the camera to say it's a pass, the robot will take the camera to the next position and do this. So it's a completely seamless installation. This is by a company called RoboMinds in Germany. And this is quite prescient because we've just applied robots into COVID sorting applications. And this robot's been set up to do something similar. So there's 2 robots working in harmony here. On the left-hand side, you will see like a 3D bin when the samples arrive in a random fashion. There's a 3D bin picking application that tells the robot where to go and vacuum pick a part. It'll then drop it into a little backlit panel. And then the next robot is looking at the camera or receiving images from the camera above to go to its pick position. It'll then determine the color of the vial and the size of the vial, and then put it into the correct nest where it needs to go. So these 2 robots are working side by side. They're also sharing their coordinates by Modbus so that they can't bump into each other. So this is kind of task balancing a sorting application. And when you look at sorting of testing for blood analysis and things like that, the real choke point is a lot of the times is getting these samples from a random position to a known position, put them into the racks or order, and then they can be inspected and checked for. So this is something that's being done now. It's actually leading on to the PCR test for the COVID in the UK, where it's actually being presented to a camera system and a barcode's being read, and then that data tells the robot what position it's got to put it into. Thank you, and that's all from me.
Thank you very much, Mark, for a great presentation. It is fantastic to have the end users telling us where the cameras are being deployed. This is an epic meeting, so it's a meeting looking for cooperations. We want to help you make your cameras better for your customers. So do you have a couple of challenges, a couple of ideas, a couple of room for cooperation with the rest of the supply chain?
Okay, so one of the things that we have at the Universal Robots is something called the UR Plus scheme. And the UR Plus scheme is like our version of Apple's App Store. It's all the devices that are plug and play compatible. Now we are continually adding to this, and vision systems, we only have about 23 vision systems that are plug and play compatible. We're always looking for extra vision systems to go into that, or bin picking solutions, or 3D inspection systems. Once you become UR Plus certified, we then put your products onto our website and you get promoted globally. So any of our partners can have access to that. So it's in real interest to get products UR Plus certified. We make no money from it, but we freely promote it. And our idea is for everybody that wants to use an application and make it easy, if they can buy a camera and it just works and it's compatible with the robot, then we'll sell more robots. And that's our whole ethos of the UR Plus scheme.
Mark, this is great. Could you put the link in the chat later? Could you put the link in the chat? We all want to hear it because we are gonna fill this database. You will see. I'm gonna try to get all the companies that I think are really interesting for adding vision functionality to your systems. I'm gonna go first to Belgium. I'm gonna go to imec. Wouter, what can you do for Universal Robots? In general, what do you do?
Hi, nice to have me. Thank you for having me here. So let me share my slide I prepared for this meeting. So we at IMEC are making hyperspectral sensors on chip directly. So that's what makes us different, I think, from other hyperspectral imaging providers. And what is very unique to that is that we can, by doing that, miniaturize a lot the hyperspectral chips or hyperspectral systems and make them much more low cost. And specifically unique is that by using our CMOS patterning devices, we can pattern filters on a single pixel. So that means that we can make a sort of Bayer pattern on grayscale imagers and can really make hyperspectral video imagers. So that means that we don't need to scan, and we can have a snapshot way of acquisition spectral data. So when I'm thinking then about robotics and bin picking applications, or also in where robots cooperate with other humans, then you can have a motion, you can capture the data while in motion. So then you can do real-time classification or object detection, or taking real-time decisions based on the images that you capture. So I think that's something that can be very interesting for robotics applications, and yeah, where imec can really contribute. So I was very interested in hearing the presentation. I would also like to hear if there are some opportunities that can be identified in that direction.
Mark, how does Wouter proceed now? You have you muted, right? We have you. Let me see if I can unmute you. Yes.
Yep. So the best thing to do is to go to our website, and there is a section of that called UR Plus on the website. And if you scroll down to the bottom of it, you can actually access how the process to become a UR Plus supplier. So you'll make contact with a German gentleman called Christian Fenk, and he'll guide you through the process of what you need to do to become UR Plus certified. Okay.
And, do you see any gaps in the offering of UR Plus that would make a good case for hyperspectral, or any applications that would specifically benefit from this?
It's quite a specialized field that I guess it would depend on the applications. Maybe, I mean, if you're looking at particular industries where that was having to manipulate that sort of camera with a robot, it would be quite specific, I guess. But I can tell you we don't currently have hyperspectral imaging on our UR Plus certified system. So it would be well worth you going through that process, and you'll learn exactly how the process works. Like I say, we don't charge for it. Basically, what we act as a liaison between how your software will integrate with our software and to make it compatible. And then once that's done, you then become certified. And when you're certified, you'll go on the website.
Okay.
I think one of the reasons why you don't have hyperspectral imaging there is because of the unique selling points that Wouter is covering that were not covered yet. Yeah. And I think that's a huge opportunity for Wouter to collaborate on this. And on that respect, I think Jan from Caeleste has something on his mind. Jan, I see that you have a couple of questions.
Yeah, my main question, in fact, to Wouter is, what is your business model? How are you going to disseminate or distribute further the technology?
Okay, so we want to bring this technology as close as possible to the application. So because by our core technology is really just the filter that we deposit on the chip, but we need to put this in the hands of people applying it for applications. So then when we make people successful with our technology, they will come to us and say, now I have tackled this. And because we have the infrastructure to do the mass manufacturing and make it really cheap, we can enable these applications that could not exist today. So this is what we're after. We want to really put this in the hand of people to then get these the larger volumes realized. Because I truly believe that there's a whole range of applications requiring video mode imaging that are currently not existing because the technology has not been there yet.
Okay.
So I have companies in EPIC, well, R&D, RTO centers in EPIC like imec, ACM, VTT. They all are developing very innovative, suitable to volume production hyperspectral imaging systems. I expect that there will be, Wouter, I actually expect this, there will be spin-off companies out of this, and I know you cannot say it, but this is my hope. I think it will happen relatively soon. I'm going to move on with the program. It's been so interesting so far, but hang on to your desk. What's coming now is really interesting. Video hyperspectral cameras. Oh, Cubert, I really love this company. They work very closely with Delta Optical Thin Film. Oliver asked us to put you on stage, and for us it's a pleasure. Thank you very much, René, for being with us this beautiful afternoon. Tell us about video hyperspectral imaging. The floor and the attention of everyone goes to you.
Hey, thanks a lot. I really appreciate that we can give a talk today. And I try to tell you a little bit more about the applications. I think I have given a talk like half a year ago at EPIC, and roughly, and I introduced the hyperspectral imaging which Cubert is doing, and I didn't want to reiterate the same talk, so I'm much more focused on applications today, and especially on how the application made us innovate our technology again. You should see my screen right now. Yeah, okay, thanks. Yeah, at Cubert, we are doing hyperspectral video imaging, pretty much like imec is doing. However, we are using a little bit different approach. imec is bringing the filters directly in front of the pixels. And we detached the filters and built them into what we would call a light field approach. So we can use dichroitic filters, which can be a little bit more complex than what you can bring to a pixel level. And Wouter, please correct me if that's not true. Okay. So, however, our devices are not as small. So I think Wouter's devices are really, really small, the smallest you can get. Our devices, our technology at 7 millimeters thickness to the camera. So I think it's still comparably small. Yeah, and what our customers are doing, this is just one application. Robert Bosch is working on precision agriculture, and they are interested in measuring different plant disease with one measurement device. The typical multispectral camera usually just gives you the information if a plant is sick or if it's healthy. And what we want to add to the table is to inform you, is it a fungus or some other disease? And what you see here is first results we got from that project. In the confusion matrix, you see that we can have a 97% correct prediction if a plant is healthy. And then we have a discrimination between different disease. However, yeah, one disease is still tough to tackle with hyperspectral, but we just started. And the goal in the end is to have a truck and to provide the plant protection only there where you need to provide it, and even to go with 2 different detergents at one time, and yeah, to save plant protection fluid, save money and save the planet, so to say. Yeah. And the problem with that usually, or I mean, there's a challenge how to collect the data. And if you look at hyperspectral imaging systems, I found a nice graph here from a colleague, which is listed here, who did the work for me to depict it. So you can have a push broom device, example given, and then if you go flying, then you have to put all the lines together, which is typically possible if the plane is flying in a very straight line, and if you have very good equipment, IMU, very, very high quality IMU, GPS and stuff like that. And I think also Resonon solved that, so it's definitely possible, but it's a problem, it's a challenge. And it gets much easier if you do something like we like to provide. You provide a camera which acquires just the whole image at one sensor readout. Meaning, in our case, we have in flying conditions something like 3 milliseconds integration time, and in the time we generate the whole cube. So you always end up with an image, and can do your post-processing from there, skipping the IMU and GPS part. And yes, this is the top thing here. This is the camera we started last year, which is called the Ultras S20. It's a 400 by 400 pixel hyperspectral camera. It has 100 channels. And what we added this year, and this is especially due to the drone application, is another 5 megapixel sensor. So what we do here is we do data the combination of these data sets. So we have a really high resolution. And with that 5 micropixels pan sensor, which is especially used for positioning of the camera, we can do a drone integration, and the drone integration doesn't need an IMU, it doesn't need a GPS, and it doesn't need a gimbal at all. So bringing down the complexity of this whole system. Each hyperspectral image looks something like that. So this is what I talked about in a capture of 3 millisecond data. So it's a lot of data, it's 160,000 single spectral points. To be fair, the Resonon systems have better signal to noise ratio, but we are faster. So anyhow, what you can get is you can calculate from these data sets different data results. For today, I just go with pseudo RGB, meaning I take from the whole cube, which I captured before, just 3 colors, and generate an RGB pixel. And what you see here is a 400 by 400 pixel image. And yeah, it is an image, but it looks still a little bit blurry. And for positioning, you don't have the highest precision of positioning. And therefore, we added this 5 megapixel sensor. Whoops, sorry. Going back. So, and if you do data combination of both, then you end up with a pretty awesome end result. So it's a megapixel hyperspectral data set, which is, yeah, measured in a few milliseconds. And yeah, we were stunned by the image quality, to be honest. So I was expecting it to be nice, but it's even, yeah, sometimes you're lucky. And what we can do then is we fly a drone, and this is a flight path of a drone, and then combine multiple images just with a stitching technology, which is pretty regular today for photogrammetry. So there are plenty of softwares which can do that. And so you end up with a hyperspectral camera using the same tools every other person is using, which makes the processing much easier. And in the end, you can acquire huge maps, and yeah, with pretty nice resolution. So we are down a typical flying heights to whatever, 2 centimeter resolution or something like that. Yeah, and that's and it's easy. Did I mention that it's easy to do it? So that's pretty much it. And yeah, thanks for the opportunity. If there are questions from your side, we are always happy to talk. And I forgot one thing. We are also very interested in bringing the price down. So this is the whole thing of this miniaturization. I think it's leading to better prices, and I think that's where the market is going. Okay.
Thank you, René, very much for this great presentation, as usual. I'm sure there will be a lot of question comments. If not right now, then in the future you will receive all of them. But one where we always start with the question, what you can do for them and what they can do for you. So the epic question, what would you say? To the epic question, what you can do for them and what they can do for you.
Ah, okay, that was a question to me. I was a little bit confused. What we can do for epic? Or sorry, I didn't.
No, what you can do for the community, for people who are in the room today.
Right, okay. Yeah, we are interested. As Wouter already mentioned, I mean, it's in part the same discussion. These video spectral imagers are typically meant for robotics. So every robotic application is of great interest to us. It takes a little bit of the complexity away, and also the size is much reduced. And I mean, the robots don't have to carry that much. And overall, I hope we are heading with a very different approach. I think push broom spectral imaging is a great approach for a lot of applications. already solving a lot of great applications, but with bringing this video spectroscopy to a market, we just provide you with a possibility to innovate. And where see us heading is providing really affordable systems as well, not only systems for scientists.
Okay, thank you. Well, let's see what the supply chain can help you with as well. We have Ralf from Leopil here. Ralf, would you introduce yourself and tell us a little bit about Leopil and what you're working on and what you have on the offer? And also please unmute yourself because otherwise we won't hear it.
Okay, unmuting first. Hello, everybody.
Perfect.
And second, let me see how I get to...
At the bottom?
Yes, and then I just have to see it. All right, well, does that work? No, it doesn't. Anyway, I tell you, while I figure that out, I tell you what Leopil is doing. That would be a slight switch from the super high resolution and recording imaging rather to projection imaging and to what we feel is sort of the lower end of resolution, which would be something like VGA resolution. And of course, my question with this is, when we manufacture those things, is there any application for it? Is there any demand for lens elements and lenses of this type? Let me see.
René, do you have any demands on optics, on lenses, on instrument design? Leopil is a key company.
We have
in the
demand
design of instruments.
on micro lenses or micro optics, and other than that, we don't have a special demand on lenses. So there we typically buy lenses from suppliers like the typical suppliers that you have.
Okay, so if we were to make glass lenses with microstructures on them, for example, to correct for chromatic aberrations.
No, I'm really talking about micro optics, like lenses which are 0.5 millimeter thick.
Oh, okay. Arrays and things like that.
Micro lens LED arrays. We are heading down the miniaturization path with our technology.
René, you know that Europe is now living the revolution of micro optics. This is like the biggest thing that has happened in Europe in the last 20 years. If you're looking for any free form shape of a micro optic, come to EPIC. We have the whole community looking forward to helping you, and we even got money from the European Commission to do so. So please, any company, I want to ask any company in the world now, any challenge of micro optics, come and speak to me or to Sana Pica, of course, or to Elena Beletkaia. René, you are making video hyperspectral imaging systems, which is great, but you collect a hell of amount of data. Isn't that a huge challenge, the data processing in your cameras?
I think we can handle it quite well. So the data processing we are doing on the cameras at the moment takes something like 50 milliseconds. So meaning we are capable of having a video a result stream of 20 hertz or something like that. So yeah, it's a challenge, but it's tackable due to the processing power of modern computers and microcomputers.
We have now the images of the DOEs from Leopil. Tell us, Ralf.
Well, thanks very much. So we would use a glass lens which would have basically any pressed shape, so not very accurate, but having still the advantages of glass. Then we would coat it with a DOE optical element, for example, for color correction, and would also be able to create a full lens of it with given field of view and things like that. So we have a few applications. which we cannot show. But of course, we are interested in seeing whether there is this type of low-end color-corrected projection lens application in what you're doing in machine vision. Anybody, any ideas?
I think this is better to be discussed offline. So any company that want to interact with leopil in this particular challenge and applying DOEs to any camera system, Ralf is the person to go. I also want to talk to Martin from EVG. So Martin, isn't it right that Europe is now leading the revolution of micro optics? EVG in Florian Anin is one of the key companies in that sector. Martin Eubelhuger. I think while we prepare, Martin, I think it's good to continue. We have two questions.
1 second. So
yes,
I'm muted. Yes, you're correct. So as Jose, definitely here in Europe, there's, I think, worldwide main activity on micro optics and definitely the manufacturing. And yeah, always happy to discuss about it if there are any questions.
We can do this wafer level micro optics on glass or polymer, and we can actually even have the equipment for the volume production. It is unique, and EVG in Florian Anin is one of the key companies in this sector. I have two questions in the chat. The first one is coming from Chris, the president of EMVA.
Thanks, Jose. I'll jump in and ask it myself. I was just interested, we have three different modes of hyperspectral imaging providers, essentially. We've got push broom, light field, and filter on the chip. I was just interested for your respective customers, what they're actually coming to you with, what's their top concern, whether they're aware of the trade-off of spatial versus spectral, whether it's just cost, whether it's ease of use, because there's three different views at least I would expect here.
I think for us, it's let's say it that way. I think we have the niche of providing easy to use spectral imagers. So I guess most of our customers are interested in high quality spectral data, but also combination, which is easy to use in the end, and especially in the robotic applications. Push broom sensors might give you a challenge.
Yeah.
And as soon and I would guess maybe also the price is one restraint. However, we are providing plenty of cameras to high quality applications where price is not so much a constraint, like Rand already told. So as soon the you can save enough money, then price of the camera is not a problem. But I guess that the hyperspectral imaging companies restrain their potential probably by the high entrance price, and I am pretty sure when we can lower that also other applications which are of less financial value.
We have another question in the chat, and we're going to help you make your camera better, René. We have another question in the chat. We're going to go to Finland. Philip Monoyer from VTT. Philip, can you rephrase the question? Because I don't like to talk about cost. I prefer to talk about making things more cost effective. Philip.
Well, what we just said before relates to also the description of the ideal hyperspectral camera. And I think it should be mass manufacturable. It should be free. It should cover a huge wavelength range from UV to long wave infrared, and then it would be infinitely fast. So that camera doesn't exist. So also customers would like to know what are the use cases, because they obviously know that this is so interesting for so many things. But it's an exploratory phase now, and the market is exploding. But essentially the price, the wavelength range, the speed, and probably also frame-based is desired. As much as you can give in the same envelope is the best.
Yes. Yeah, the problem is you have to solve the price, the speed, the high integration, the ease of use, blah, blah, blah. And then people tend to buy one camera. And then a year later they buy another one, and a year later they buy another one, and then they want to have these cameras perfectly the same. So which is problematic, and which gives you gives you a struggle, and you have to solve somehow this. You have to open up the market. We cannot provide very affordable cameras when we have numbers like 100 devices a year. That's simply not possible. So you have to somehow open up the market to have 1,000, 2,000 camera market per year for hyperspectral cameras. And then we have the technology to provide cost-efficient devices. And the issue is here that these applications you're talking about are, as you said, in an explorative field, except probably some sorting applications, which are already solved by head wall, Resonon, InnoSpec, whomever.
I think René, I think Rand and Jan want to share some thoughts. Let's start with Belgium. Jan, what's on your mind?
Yeah, I had a question. Cost effectiveness is one thing. Performance is, of course, another thing. When I looked to René's presentation, I was asking myself, what is, let's say, where's the catch? Are you not introducing somewhere artifacts in your image, perhaps motion artifacts? Can you explain a little bit on that?
No, we don't have motion artifacts. The catch is the following: we are using to have this. We provide 160,000 spectra per sensor readout, and to do that, we are using a huge sensor, a UHD sensor, which has 20 megapixels, which is pretty unique. Since typically, if you want to have an optic for such a huge sensor, then you need a lot of glass, and that would be super expensive. And with having this micro optic approach, we are able to simply use a huge sensor like that, and that's the catch, so to say. So just by increasing the pixel count, we can increase the resolution. However, and I can say that pretty openly, we are using at the moment a CMOS from CMOSIS, which has not the same signal-to-noise ratio as the CCD, for example. So we have something like 1% standard deviation, and I don't know what I compared, or I seen Resonance presentation once, and I think they have had a twice better signal-to-noise ratio to us.
I think Rand would like to comment on that. Isn't that right?
Yeah, I'll just throw in briefly. First of all, I'd like to say I really like René's technology, and it's got some super applications, and also I personally enjoy René. One difference that comes out that people were talking about that are different applications. There are certainly applications where being able to see the whole scene at once instead of push broom is really an advantage. And one of those that René didn't mention, where we've been getting some requests, and I usually shove those over to René when I get them, are like for endoscopes in the medical industry, where push broom just isn't a reasonable solution. I think a challenge that we're both facing, though, is speed. Perhaps René's up to 20 hertz, but we're seeing, I know in some of our high-speed conveyor belt applications, where really to get the resolutions that we would need to get, we need to be taking 1,000 lines per second. And that is a challenge for hyperspectral in a way we're heading to, but it is a hill to climb. And I'll stop with that.
I would like to say that we have a lot of room for cooperations here. So once again, I want to remind that everybody who wants to connect with each other for a later follow-up, they can send me an email. And also, all of you have been contacted by my colleague Suzette Germer. After the meeting finishes, there will be one-to-one meetings for the people to do business. René, I love Cubert. You know that. I love your technology. I want you here. Please, as soon as possible, send me the form. We continue with the program and we go to one of my most beloved companies, member of EPIC. We go to Xenics and we go to Mark Larive, who is going to tell us how the EPIC community can make the Xenics machines even better than they already are. Xenics cameras, the floor and the attention of everyone goes to you.
Okay. Thank you very much. Jose, can you see my screen?
Yes.
Great. Okay. Running on diaporama. You see my screen? No, it works.
No, it's the last slide, so you have to start from the
Yeah,
beginning.
no, it was the first, but that's always the case, you know. When you do the repetition, everything is working, and then when you are going live,
Here it is.
okay.
No,
So you don't see
film
anything.
2
Okay,
is the
so
last.
I will do this like this. Okay. Okay. So I'm sorry, it doesn't work. So let's do it that way. Okay.
Go ahead.
So thank you, everybody. Thank you to Epic and Jose for inviting me. So I will talk now about the vision and the industrial system. What can we do with infrared cameras in vision and industrial system, and what Xenics can give, can offer, can provide, and what do we need from the Epic and the audience. So first of all, what is Xenics and what is our activity? We are a supplier of leading edge infrared solutions. So we focus on infrared, every infrared from the short wave to the long wave, okay? We manufacture sensors in short wave, cores in short wave, mid wave, long wave, and cameras from the short wave, mid wave to long wave, okay? And we are, let's say, focused on providing the industrial people the right solution. And we focused on market segments such as machine vision, process control, safety and security, transport, medical, and of course, R&D. We have a large portfolio, more than 10 product families with different products inside. And we cover, as I said, a broad range of segments. As an example, we offer the highest speed. I mentioned that, and just a few minutes ago, people ask for high-speed cameras. So in infrared, we have the highest speed camera for line scan with a 2K line working at 250 kilohertz full line. And we also offer the fastest camera in 2D array for short range with a VGA format running at 1.7 kilohertz full frame. So that the highest speed you can find on the market, and that enable a lot of things, including the kind of application that has been mentioned previously. We also provide some, on the other side, let's say, ultra compact, ultra swap, that means optimized in size, weight, and power, VGA long wave core. I think this is the smallest and the lightest of the market. It's only 6 grams, 800 milliwatts of power consumption, and with the ability of running shutterless with good stability. So all these cameras are offered for the, let's say, to the user for the all kind of application. And let's say we focus a lot on high volume and on industrial application. We also have very specific product, but we try to offer to the wide market the highest quality and highest capabilities you can get with infrared cameras. So what can the infrared vision give? We spoke about visible just in the previous presentation, impressive presentation about hyperspectral. What the infrared can give as benefit for the user. So the infrared can give a big help in seeing inside, seeing what, and seeing ahead. So typically, when you want to see inside, depending on the application and the material, but for semiconductors, typically silicon is transparent in infrared, in shortwave infrared. So with a shortwave infrared camera, you can see what is inside your wafer or your chip. Typically, that's what the picture will show you. You have the visible picture and the infrared picture. So in infrared, you can see really inside. You can check the alignment at the micron level. You can see the crack and the material, well, whether there is a problem in the process, then you can check and see it. The shortwave also has the ability to go a bit deeper inside the tissue than the visible. So typically it's of great use for optical coherence tomography for medical application. So these are real examples, and also for fluorescence when you want to monitor some, let's say, biological materials that you are checking, then by fluorescence, with the short wave, you can see inside. But with the short wave, as we said previously, with the hyperspectral and spectroscopic materials and so on, you can see also what. And this is a lot of help for a lot of kind of industrial process control or quality inspection, such as food sorting, where you can just detect whether it is a real grain or whether it is a stone on a screw or let's say pieces of glass inside rice, for example. But also you can detect the quality for meat inspection, for example. And you can also check the material for recycling when you want to make difference between different kind of plastic, because the recycling process will be different. So this is what you can do with shortwave infrared. And it can also help to see ahead the infrared, either in shortwave or in long wave. For transport, typically it's used for enhanced vision, and also with gated camera to see further through the fog or through this kind of thing. So what's next, in fact? What are the following opportunities? We in Xenics have a lot of products that fulfill the current application with what I presented just before. But what is the next step? We have a lot of opportunities, typically to improve the wavelengths in shortwave. There is a standard one from 900 nanometer to 1700 nanometer, but perhaps you need to go more on the visible side, or on the other side, you prefer to go further than 1.7 micron. You perhaps need to go 1.9 and 2.5. So this we are working on. Also to increase the resolution. I heard about the discussion about resolution just before. This is something we are working on, and we are looking for a trade-off between the format and the other characteristic. The other characteristic of the camera can be either sensitivity, either speed, but also the cost. So this is a lot of work to be done. Also the adaptation to specific need, as people mentioned, I think Resonon, you mentioned that there is a need for more spatial resolution and perhaps less spectral resolution. So in this case, typically a 4:3 form factor, is perhaps not the best solution. So we also are working on it, and also on the way to reduce the price, the cost of the cameras. Also, the cost has been mentioned previously, but in order to optimize it, what can be done? Where can you select the good or the bad pixel if there is a need of something very good in the center and not on the border or the reverse? Then that's something we can discuss. Embedded filter on chip, that's also a subject that we are working on, and a lot of discussion about adding intelligence on the camera and the sensor, and that's a very difficult task because we are just camera manufacturer. We are not user we will not apply this tool to the production itself. So we need to discuss with the user to understand the best solution. So typically what we need from the community and from the customers is what are the technical needs from the user, and also, as Cubert mentioned, what is the business for it? So we will be able, with this discussion, to set up the next standard, the next product. Okay, so thank you very much. That's all I wanted to talk to you, and I'm open for discussion and to answer any question.
Perfect, Mark. Thank you very much for this great presentation and introducing us this time to a different type of camera and imaging. There are some questions. Let's address them first. Anders from ASE Optics, would you like to ask your question?
Thank you. No, I had not a particular question in mind. I was just commenting on some of the chat questions that were asked before, but thank you for that great presentation. Appreciate it. Actually, now that I do have one question, I was going to save it for later, but you mentioned that there was some cameras that you were developed that have use in OCT. What kind of do you have linear arrays for that type of application? And what kind of velocity or frame rate can you get from these?
So we have, let's say, basically in OCT, usually people want speed, high speed, and also high resolution. I want everything.
Of course.
Okay. So what we have and which kind of cameras that we manufacture are used in OCT. Typically, it's the high resolution and the high speed. So the last product we launched this year is the Manx. It's a 2K line, which is able to run at more than 200. I said 256 or 53 kilohertz.
Okay.
Full line. But we also that's for spectral domain and for the classical one. We also have the Cheetah, which is a VGA, but you can run the full frame at 1.7 kilohertz. So that's probably for special domain, but it is also used. But let's say the most obvious regarding the current systems are the 2 kilopixel line.
Okay, thank you very much.
Welcome.
Great. Well, thank you. You see how it worked out. You just need to start speaking, and there you go. You have a question. Let's try it once more. Mark from Demcon. Would you maybe have a couple of challenges to us, well, not to us, but to everyone in the room, or maybe someone specific?
Not so much challenges, but from Demcon. Demcon is a key company in the system integration in EPIC. And I really would like to hear from you a little bit what kind of cooperations you could do with the companies that we heard so far in the meeting, Mark.
Yes, thank you for having me in the first place, of course. Look, Demcon is a system integrator, as you all know, I hope. We mostly have specialized in high-tech applications on bespoke optomechatronic systems. So I do not have any challenges at the moment which are specific to this topic, but we're almost always in this field, of course, in the optics and the optomechatronics, vision, artificial intelligence, or whatever other topics that are relevant in the EPIC. Yes.
Okay, thank you. Thanks for sharing with us. That's always nice. I believe we will be moving now further to a next presentation on our agenda. Udo from Pozo. The attention of the audience and all eyes are going towards you.
Yes, so for the moment, I still see the screen of the previous presentation, so maybe he needs to go out.
That might be a delay in the video, because for me I see all the rest, but let me double check that we don't have others shared. And
Okay.
It should be okay now. Go ahead.
Yes.
Okay. So my name is Heinzel. I'm CTO of Pozo. We are in Switzerland, and the company was founded in 1943. So our vision for the business is we are a machine tool manufacturer, and we offer micro machining solutions to our customers. Our machines are very known for their long-lasting quality and reliability within mass production environment.
Sorry, Udo, are we supposed to be seeing some slides from you at the moment?
Yes.
Because we are not yet, and we are super excited about them because actually I have seen them before. So please try to go to the bottom of the screen when it has the green arrow and press share screen there.
Yes, but this is what I did, so I will do it again.
Maybe you need to choose
repeating is the art
share.
of mastering, so we will
But
manage.
then when I do that, I'm not able to select at least what I want to share.
You should get a pop-up screen, but I think we can really solve it. I'm gonna share the presentations from my laptop, if that's okay, and then you can tell me next slide.
It has been changed. It has been changed. So this could be that I can.
Okay, let's try again. So you go to the bottom of the screen, share screen. It will ask you which screen do you want to share.
So partager.
I think we're in business. I think Switzerland is bringing us the imaging from Pozo. You are sharing right now your email, so we don't want to look at that.
Okay. That was my boss. So
he's doing a really good job. Pozo joined Tepic recently. Thank you very much for your support.
PowerPoint, do you see now the...
Yes,
we
you can go full screen
now.
Yes.
Yes, so now I need to switch up. And just push there, and then I need PowerPoint presentation mode.
And we solved it. The floor is yours.
Okay.
Yes.
So I was at the vision. So for us, we are. I need to get this away. So a machine tool builder, we are known for our long-lasting quality and reliability within mass production environment. And of course, our aim is that we are market leader in the areas we are going in. So the business areas are in the automotive industry for injection system market. Here we have different technologies available. We have the EDM, electrical discharge machining. We have the femto laser technology, but we also do mechanical milling. And in the world of electronics, we are active in the test equipment market with the femto laser technology, but also on the printed circuit board market, where we do drilling and routing. These are mechanical machines. And then we have what we call plus. Plus at least needs to be a new application in a known market, or if it's a new application, or if it's, a known application for new markets. The femto laser technology, we offer typical mono machine. It's the femto mono. It's a 3-axis machine. Now we see the component layout. We have on the bottom a XY stage. And then we have for the Z-axis our 5-axis scanner and the vision system, which is integrated with or near to the 5-axis scanner. For automotive, we mainly have 5-axis machine. It's here the femto twin, and we have here 2 stations. With these machines, of course, we have needs for the automotive applications. What we have to do mainly is to guarantee the component traceability. Means we have at one time to read a data matrix and to be sure that the machining we do is then linked to that part, and the part, these informations go later on in a MES. What we also do with the vision is we have to identify angular positioning of the parts. So we have to detect the laser marked or mechanical marking. And yeah, this has to be done. It has to go fast and gives the part orientation for the machining. And typically for the automotive industry, for the gasoline injection, we have to drill some spray holes. So we use the vision to align the physical machined step hole, and then we correct the positioning of the part in order to be able to do a perfect alignment between pre-machined step hole and to-be machined spray hole. The challenges for the vision systems are, from our point of view, the contrast for detection of physical blind holes, laser marked dots or circles or whatever. This is a key issue to overcome. For example, the picture on the right, it's a laser marked circle on the substrate, and you're looking for that in order to define the part positioning. We are also very sensitive to lighting conditions and, of course, to the projection angle of what we are looking at, because the parts are not flat, they can have a cupolino and so on. So, for example, these are two pictures taken from the same part, but with slight changes in the setup of the vision system. And yeah, for the vision itself, it has to be successful at 100%. Every time we have an issue in part recognition or individual identification, the customer loses the part and it's game over. And then there's also a question of rapidity of the treatment, taking a picture, recognition or running through the algorithm and give back a result has to be done within less than 0.2 seconds. So these are the challenges for the automotive industry. If you look now at our electronic applications, we are in a 3-axis machine, and the customer workpiece is flat, and it's on that XY stage. We have a working field of 300 by 300 millimeters, and the customer can define different working fields where he will position the part drawing he wants to execute. And this is a pure theoretical exercise. But at the end, what we need to do is use the vision system to know exactly where the part is positioned physically on the table. So the customer parts, they have reference holes. We have one hole for the XY localization and the second one for the angle. And at least with precisely detecting of this positioning holes, we recalculate the drilling jobs, and then we execute tens or hundreds of thousands of holes, which are then machined and positioned accurately to these reference holes. The challenges we have for the vision systems is at least the accuracy. When we take the reference holes, we have to achieve an accuracy within ±2 micrometer. The range of diameter for these holes, it can be a few tenths of micrometer, but we can go up to 3 millimeter. And for that reason, we have to use different lenses. And we also have to be insensitive regarding substrate colors, because it has an influence on the contrast. And if you want to look at very small holes, at least we very often use backlight. So that's all from our side in Switzerland. Sorry for the difficult start.
Well, it was a very great presentation. So it smoothens out the difficulty at the start. And thank you very much for showing up so many challenges for the vision system that you have. Let's see if we can solve some of them, or at least find possibilities to solve them. We do have in the room ACM Coatings, and I was curious to address maybe some of these challenges there. Can you show yourself?
I'm here. Hello.
Okay, perfect. Alexander, thank you for joining us. And maybe you can tell us a little bit more about ACM Coatings and whether it could be a partial solution to the contrast issues, lightning issues, or other issues which we heard at the moment from Pozo.
Yes, so thank you for the short introduction. My name is Alexander Teller. I am the CEO of ACM. We are the German subsidiary of ACTA, and we are specialized in black coatings to absorb stray light, scattered light, unwanted light in optical systems, also to prevent crosstalk between illumination path and sensing path. And the special thing about our coatings is that we absorb a broad wavelength range of light. So not only the visible light, but also in the UV and infrared, we are able to absorb 99 and even more % of the overall light. So everywhere where you have a stray light topic that comes from reflections of internal structures, mechanical, optomechanical structures, our coatings are used to prevent that. And we do also produce apertures, for example, stray light apertures to suppress the stray light in the system.
Okay, thank you. I have one question to Udo myself, because you were talking also in your presentation that the speed is playing a very crucial role. So could you also give a little bit on the a feeling of what speed are we talking about, how fast the process needs to be made, how fast the camera has to be reacting?
So in fact, if we look at the automotive industry, we have that part. It's called the valve seat with the step hole, which are already machined by milling. So we have it in a truck, and then we have to present the part under the camera system. And of course, per machined step hole, we reposition the part, and then it has to go fast because we move simply to the next step hole, and so we expect the data back with less than 0.2 seconds.
And then similar question as was before, then also when you work so fast and you go through so many data points, then it also would require a solution for the data, for managing the data. Is that also something you're working on too? So
yeah, it's a combination. At least the lighting is very important. You need to achieve to have a contrast. The parts can change. You have different type of parts, but the main challenge is being fast and have the best possible contrast and having it stable over time. So then you can run with different models. If you don't catch it with one, you go in an iteration. You do changes in the setup. You try to redetect at least the geometry you're looking at. So looking at a pre-hole, if it's not machined tangential to the surface, it will become an ellipse. So you're looking for circles which are in fact seen as an ellipse by the vision system, and so on and so on. At least I think a lot of end users are struggling and find something reliable and robust. And yeah, it's just something which has to happen before doing the machining. So it's it has simply to work, and nobody will accept that some issues can happen with that.
Perfect. Thank you very much. Well, I'm sure that there will be a lot of connections coming to your way after this meeting and later on. But now let's move to the final presentation of this meeting. It's from Eric from Wageningen University, who will tell us about the challenges from agri-food robotics, challenges to vision system. Eric, if you would unmute yourself, please. And
I did.
yeah, perfect. I can hear you now.
Yeah, I will share my screen.
Let's get to your great presentation.
Yeah.
I'm sure everybody is very excited about, at least I am, very much.
Yeah, let's see.
We see your screen and your presentation.
You see my presentation, yes. So that's good. Thank you very much.
Perfect.
Yes, so I'm not from the cameras and from the hardware. We are a little bit more from the software and the application, though I saw most of the cameras already from Cubert, from imec we are using as well. So we have some connections at least. But I thought it would be good to show you a little bit what the challenge is in agri-food. So that's our business. I've come from Wageningen University and Research. I'm the program manager on agri-food robotics, who is dealing mostly within Wageningen with machine vision applications. And from that perspective, we have a great challenge to face, is that we see the ag employment declining on one hand, and it's also a situation, if you look to China, for example, from the 90s, they already reduced from 45% to 25% labor force in agriculture, but they expect to decline to 5% in 2042. And yeah, in the world, we still have 2 billion people who are doing agricultural work, and those farm workers are now moving to cities, and we don't have them anymore. So, and a lot of these tasks are monitoring, are handling of food products, and we are really challenged there. So how do we gonna save all these jobs, because they are simply not there. Also in the Netherlands, we did a study, and 80% of the farmers cannot find enough labor, and not the good quality labor. And we lost the Polish. We are now moving further away to the Ukraine. And that's a situation we are facing all over the world. Also in China, people are moving to cities, and also the rural area is not only declining in the workforce, but it's also aging. And we see the same in Europe. Also, the workforce in agri-food is aging. Much older, younger people are moving to year-round jobs in cities. So this is also, and now I come back to Wageningen University and Research. So we have a team of 40 people active in machine vision applications, researchers in the research domain, and we have the university as well, and it's almost a similar group, a little less, but we are together with 60 to 70 researchers active on agri-food, machine vision and robotic applications. And we divided in our team we have vision experts, more the geometric features, 3D reconstruction. Then we have the spectral people who are active in chemical compounds, disease detection, all quality sorting machines. Then we have the AI people who also look to seasonal changes and how to do the monitoring in that sense and make decision rules for it. And then we have the robotic systems. And it all comes to the markets. And I think it's, I thought it showed a little bit like an internal presentation, but I think it's actually not, because I think these are also the questions raised by the agri-food sector. So where we see most activities is in breeding. And then not only breeding performance of plants, but also breeding performance of animals. How do our chickens move? Can they still walk, or is it only kilograms what they produce? Are they happy? And on the plant side, we would like to connect the phenotype to the genotype. Genotype is expressed in data already, but the phenotype is now moving to also data. And then it's very interesting to connect the genotype with the phenotype. And we have many, many projects, because you would like to detect seeds, small plants, bigger plants. Then you do the upscaling, small fields, bigger fields. Then you want to have the connection from the consumer back. So breeding is a big program for us, and we have hundreds of applications in vision there. Then we have the circular agri-food system, which applies more for the precision agriculture. So mounting cameras on our harvesters, on our weeding machines, on drones, to monitor what is the current status in the field, and also to make yield maps. What do we really harvest per square meter? And that's why you have to do it on the harvester itself, so that you can make these correlations, and then you can do the precision agriculture much better. Third is hands-free. So everywhere people are touching products, and in horticulture, they are mostly touched twice, at harvest and at packaging. We are replacing that by robots if possible, to avoid contamination, to secure track and tracing, and to save a lot of cost. And then at the end, we have the objective product and process quality post-harvest. So when it is harvested, then we have a lot of work to do there. Do the bin picking, composing, ready meals, including up to the retail, packaging in supermarkets where we need a lot of machine vision applications as well. Altogether, we could put it in basic research, but still then it's not taken up by the by business. So we also thought it would be good to have at least a proposition on this market as well. We also run ecosystems. We coordinate, for example, the agro-food community in Europe, which is a network of digital innovation hubs, but also the smart agri hubs, where we also bring small and medium enterprises and bigger companies together to discuss these kind of topics and make solutions together with university and research. So that's our domain. I thought it would be good to provide a few examples. I hope you can see it. So this is weeding, and there's also a little bit the evolution of what is happening if we are doing this. So this is a machine with a lot of cameras underneath, but we just used it for weeding in the past. Then breeders came to us and said, well, that's interesting. We do not need a device. We would like to capture the whole image of the field. And the next stage is we brought it back again to the farmers, and now we are not only using it for weeding, but we provide a full yield map of all what is happening in the field, and we measure the growth, we measure weeds, and at the end we also combine all the data from this machinery. So we always track 20 meters of a weeding machine, and then we try to learn from one to another crop. And eventually, and we are not there yet, so the other ones are all implemented and in practice and expanded, but eventually we also would like to catch diseases and in every stage of the process. So we are very much looking into that as well. Then the other side of the spectrum is 3D, and do full 3D. So not only a 2.5D image from one side, but do the full reconstruction of plants so that you can count every leaf, and because a plant will grow exponential. So if you do not have the correct size at the beginning, and we can do it very fast. So in 45 milliseconds, you have a full reconstruction of your plant with 10 cameras around it. And then you can distinguish in the stem thickness or count the leaves. These are different components we can count. And then if you have the 3D full reconstruction, you can also control robots and send out a 6 degrees of freedom robot to do the actual cutting. In this case, it is genotype cuttings. Some other interesting thing is simulation, because we also you can buy a robot, and then you have a simulation package which goes with it. But then you want to harvest crops, and where are the simulated crops? So we also work a lot on a simulation of crops. This is just captured by images. And then together with a lot of other images, we can reconstruct crops. And you can also see here, so this is a camera setup. It would be nice if it could be provided by the image companies, but now we made our own illumination together with the camera to make a simulation of our plant and what could be the best approach to finding much as possible fruits in this case. And this is only one plant, but we can also make a full reconstruction of a greenhouse. And this is a drawn picture, but then segmented so that you know exactly what the bell peppers are, the stems and the leaves. And now comes the interesting part, because on the left side, you see our picture we draw. We made it ourselves, it's artificial. And on the right hand, you see real pictures. And we try, and with the same illumination source as we did it in the simulation. In reality, as in simulation, then we try to match these pictures a little bit towards each other, and also trying to learn from one to another. So we use the AI from the fully artificial environment to the fully real environment. And you can see with only deep learning, you can also find in the real environment, just by using deep learning, all the same elements we also made ourselves in the artificial environment. So it makes it very powerful, the new deep learning algorithms, but you need very good simulation environments from that, and also same camera perspective you could add into simulation environments. This is not a picture representing. It's a little bit more vague, but it's good enough to find all the elements. And then you can make robotics also very fast and also very cheap, because if you now look to the camera, you see an algorithm which tries to find the 5 sweet peppers and also find the maximum surface. And it works quite well. It's also quite in it did find the 5 elements now, and it could potentially also be harvested, which is also very interesting, because if you are able to do it in that fast time, you have a solution, we believe, which is very robust and cheap, because now the only robot thing is the end effector. In the end effector, there is illumination, there is a camera, there is a cutting device, and there is a grasp. And the robot arm is standing exactly on the same spot normally a human is standing. And I think, then in this case, you have really viable business cases. We use the motion tracking. At the moment, we are facing some difficulties with the cameras. So we would like to have the camera full 3D as small as possible. We would like to reconstruct the whole environment. So we need multiple images binding together to a full reconstruction. And we also would like to have very small range, so that we can look 5 centimeters, so that we can also check if we detach very well on our to our product. And we would like, because the robot is standing otherwise in front of other cameras. So we have still some vision challenges, but still, I think this is a very nice way to go, and also makes robotics quite easy. So these were a few examples to show where we are working on, and of course we have multiple of these kind of examples.
Thank you very much, Eric. That's how it's done. That's how you close an epic meeting, by talking from the user perspective about real application field, like in the field of agriculture. Wageningen University is a great R&D partner for agriculture. The end users always get the same question: challenges for these people. Your Santa Claus Christmas wish list. What would you like to ask him? Sinterklaas, excuse me.
Sinterklaas. Preferably, I would like to see a camera which could reconstruct the full 3D structure of a tree or in an orchard. So it could also look behind leaves, or can at least go into the canopy and reconstruct the full 3D plant construction. And in animals, we would like to track full 3D animals. So that we can real time. And plants don't move, animals move, even more difficult, so that we can measure how firm they walk. But we have to look to all the angles. And in most cases, we only have one view from the camera's view, but that's not the other side of the plant. But by moving, especially in plants, because plants don't move, you could probably, by moving your camera, reconstruct your full environment. That would be perfect. That's one. Another thing would be very nice, at least to have also a camera which could look from a distance, but also could look from 5 centimeters and give full 3D information. We don't have need other lasers to detect if we couple. We need now other sensors to do the last bit, and that should also not be the case. Yeah.
Fantastic. I think we have questions in the room. Any question? I think
yes, there is a question from Philippa from VTT.
Yeah.
Yes,
all the way from Finland. Yes, tell us.
It was just a question about the phenotyping. I was curious. Only one part of your talk, but what spectral resolution you think is important to have when doing phenotyping?
Yeah. What do we want to look for? Huh? So when we, I think the geometric features are even more important to count leaves, to look for the stem thickness. You would like to go into stresses if you would like to check the spectral features. So diseases, and that depends very much where you are looking at, and that's also always very difficult. So we use a lot of spectral image analysis. But in phenotyping, your conditions are already ideal. So these are good growers. They provide all the nutrients. So a lack of nutrients will, in most cases, not be detected in at a research station for phenotyping, because they provide all the nutrients. So you really would like to look into the diseases they could occur. And the difficulty is still, because we are still not very good. I saw some presentations where they claim to have very good sensors to detect for diseases, but yeah, we are not aware of them to do it. We have a few diseases which are quite well, but also many diseases where our camera systems still are lacking. I think it's not the limit of the spectral image cameras, but it's the limit of knowledge and how do they occur. We never introduced the pattern in most detection of diseases. So I think it's a combination of spectral image analysis and also the pattern recognition, and preferably also some changes in time.
Wageningen University is always looking for many R&D partnerships. You always want to test anybody's cameras, anybody's system, so there's room for cooperation. I would like to give the floor to the last question of this epic meeting. It's going to imec. Wouter, what's on your mind?
So it's again on hyperspectral. We don't have much expertise on 3D, but I hope that you can shed some light on what is the challenges that you find as an end user of the technology in bringing this technology into the field.
Yeah, I think we are quite successful in the geometric features. So counting the plants, measuring the plants, also in 3D, the height. So that goes quite well. And then we have some basic information about lack of nutrients. So but still, if we are really looking into diseases, that's still very difficult. So we have a few now where we think this should be implemented and it should be commercially available, but it because the situation continuously changes. So you're not looking. The weather conditions change. You need to calibrate. I also could show a very nice picture of a morning picture of maize, where you see a full green field, and in the afternoon where the sun was shining, the leaf will curve towards each other, and you don't believe that's the same picture on the same day. Huh? So it's also very important to time it very well. And the biggest difference are in the field. So that's the most ideal thing to capture some diseases. But there the changes are, of course, also the worst. But yeah, I think we have now a few diseases in focus where we can apply spectral image analysis quite well in potatoes. We will try and then I think pattern recognition could add something. We are still not very active in that part, to be honest. We are
Eric, many people want to talk to you. Many people want to collaborate with you. There is a lot of room for cooperation here, and I want to come to visit you because I live in the Netherlands, and I want to interact directly with this university as an end user of technology, especially hyperspectral and 3D imaging. It has been, in my mind, a great meeting. We talked, first of all, we had the presentation from EMVA, and they gave us some market opportunities, and it was clear that the software, the AI, the deep learning, so people in the audience, there is a huge room for cooperation with the camera manufacturers of EPIC. Obviously, hyperspectral is the big trend. There's nothing to stop this. This meeting was not supposed to be about hyperspectral. It became a hyperspectral meeting because that seems to be what everybody cares about. And we had a very interesting idea from EMVA about a market trend, more spatial resolution, less spectral resolution is what the end users seem to be claiming. With the end users, we had a really nice presentation from Universal Robots, and whenever you're looking for cooperation, basically putting your camera in their robots, there is a link to actually find your plus scheme part of your technology and being able to customize your camera to their robots. The cost was something that it was between the lines appearing constantly. We had lots of different solutions on the detectors, on the sensors, and actually the hyperspectral imaging filters from imec were presented and one of the highlights of the meeting. One thing that was also very clear is that I see a huge growth for the company, especially in the S-width, but also N-width and L-width bands. And I think mainly because of the cost of the camera system, the cost of the components are decreasing and new users are coming. I love the presentation from Xenics on this with different application fields. And we ended up with a presentation from Pozo putting our cameras now in the laser systems, and the great presentation on agriculture from Wageningen. An epic meeting, but do not leave if you want to keep doing business, because we have now one-to-one meetings with people in the room. But for the people outside the room and people who want to now spend some time with their families, thank you so much for making my life so epic. It has been a great meeting, a great epic meeting. Let's keep doing imaging. Until the next time, be epic. See you soon. Bye-bye.
Bye-bye.
Bye. Thank you. Bye-bye.
Thank you.
Bye, everybody.
Thank you to everyone.
Bye.
Bye.
Thank you.
Thank you.
Bye bye.